So I'm just going to try and organise what we kind of know already. So we've been talking about binary structures. So that's the big set. That's the most general concept that we've been talking about. So that's where we have a set and a binary operation. And we've had lots of examples of that. All the number systems, the matrices, sets of functions. So that's where we have a set and a binary operation. And in the big blob around the edge, in other words, everything in the big blob, we're not bothered if the binary operation is nice or not. Now, in order to make some progress, we usually want the binary operation to be nice in some way. And just from experience, it turns out that associativity is very important. Okay, so a binary operation that's associative in general is more useful than the one that isn't. And we'll use a word now that I probably won't use very much in the future, but just for the record I'll write it down. This is not a word that you need to know, but if you just assume that the binary operation is associative, then we've got what's called a semigroup. So this is the second subset here. So these are all the semigroups. As I say, this is not a word that you need to know, but it is the official word. So a semigroup is a set equipped with a associative binary operation. So that's a bit nicer than just an arbitrary binary operation. And in fact, pretty much all the examples we've done are associative, apart from the kind of artificial ones that we constructed and also the ones that appear in Fraley. The artificial ones where you just draw a table with 3 or 4 elements and just construct a kind of arbitrary example to illustrate a point. Apart from those, pretty much every other example is associative. Non-associative binary operations are not very useful in general, although there are some instances where they are interesting, but on the whole we'll require our binary operations to be associative. So that remember means if you've got a triple of elements, you can do the binary operation in 2 ways, but we get the same answer. So we talked about associative binary operations last time. Now the next specialization, and this is a word that we will use from time to time, and that's the idea of a monoid. And I will write down a proper definition of monoid in a minute, or later this lecture. A monoid is where, monoids are special kinds of semigroups, so we're not throwing away the associativity, because we want associativity, but we also want an identity element. So a monoid is a set with a binary operation that is associative and it's got an identity element. And again, most of the examples that we discussed last week did have an identity element. So in the integers with addition, we've got the identity element 0. Yes, I will. Yeah, it is getting a bit small, isn't it? I'll write the next word big. Because the next word is the most important word in a sense. Yes, thank you for that. So a monoid is a binary operation that's a set with a binary operation that's associative and has an identity element, as do most of the examples we discussed last week. So for the integers with addition, we have the identity element 0. For the real numbers under multiplication, we've got the identity element 1. For matrices under multiplication, square matrices under multiplication, we've got the identity matrix. So that's the square matrix with 1s down the principal diagonal and 0s everywhere else. For functions on a set, we have the identity function, which plays the role of an identity element. So pretty much all our examples so far have been of monoids. Now, the next specialization, which is the one that we are going to be focused on most now, is the idea of a group. So I will write that bigger. partly because of the request, but also because this is the most important topic. So a group is a special kind of monoid. What else do we have besides associativity and an identity element? Well, we have inverse elements. And I want to motivate the definition of a group in a few minutes' time. But groups are monoids where we've also got inverse elements. So we haven't thrown anything away, but every element should have an inverse. So the inverse is a generalization of an idea that you've been using for a long time, which is, for instance, in the integers, every integer has a negative. And the point about a negative of an integer is that when you combine an integer with its negative, then you get the identity element. Or in the non-zero real numbers, every number has a reciprocal, 1 over x, such that if you combine it using the binary operation, in other words, if you multiply a number by its inverse there, you get the identity element 1. And similarly, for invertible matrices, we have inverses. Now, not all our examples did have inverse elements. So, for instance, if we took all real numbers under multiplication, then the number 0 doesn't have an inverse. So to get something nice, in other words, where everything has an inverse, we would have to throw away 0 and just keep the non-zero elements. So for square matrices, you know that some matrices are invertible and some aren't. So if you started with the bag of all square matrices, to get something nice, in other words, to get a group, you'd have to throw away all the non-invertible ones. So most of our examples last week were monoids at least. They were associative and an identity element. To get a group, you would, a fairly crude way of doing it would just be to get rid of everything you don't like. In other words, you would start with a monoid where you didn't necessarily have an inverse for everything, and you would just throw away the elements for which there wasn't an inverse, and then you would have a group. And that transformation from monoids to groups where you just throw away all the things you don't like is actually quite a useful construction. And it's called the group of units construction, and we'll talk a bit more about that later on today and in the coming weeks. So this picture is just supposed to organise what we've done so far and where we're heading, which is for most of the semester now, and indeed into next semester, we're just going to be in this central bit of the diagram where things are as nice as they can be. Okay, so we started out here. We could start making the binary operation nicer, and then if it's very nice, we're in the middle, which is the idea of a group. Okay, we ended last week's lecture by talking about identity elements. I didn't actually prove that identity elements have to be unique. So let me just do that quickly, because it's a little kind of warm-up theorem to get going. So let me just do that. So let me start, just remind you what an identity element is. And then what we're going to do is we're going to motivate the definition of a group, and then we're going to look at some elementary properties of groups and a few examples of groups. And that's going to set the scene really for the rest of the semester. But let's just go back to identity elements, because that's a central property of a group, that a group does have an identity element. So let A star be a binary structure. So I'm starting to use this term binary structure, which Fraley uses. It's not necessarily a universal term, but it just means a set equipped with a binary operation. Fraley, as I remarked in the tutorials yesterday, or perhaps one tutorial, uses pointy brackets, and I'm just using ordinary parentheses here, just round brackets, but Fraley uses pointy brackets here. So it's an ordered pair with a set and a binary operation. And let's take a particular element of A, which we're going to call E, and E is the standard notation for an identity element. So then E is said to be an identity element for star, or for A, comma star, if and only if, well, I wrote this down at the end of last time, so we're just recapping here. No matter which X in A you pick, if you combine X and E using the binary operation, in either order, you just get X back. So that's two equations. So for us, we'll always think about identity elements that work on both sides. One of the exercises on last week's worksheet, worksheet 2, asks you to consider, well, supposing E only worked on one side or the other, but not necessarily both. So you do have the notion of a left identity element, which is the first equation, and a right identity element, which is the second equation. So that's a weaker condition. But from now on, we'll always consider E working on both sides. Okay? So if star is commutative, then of course we've just got one equation here, because the first will imply the second and the second will imply the first. But in general, our binary operation isn't commutative. For instance, matrix multiplication or composition of functions. So we do need to write down both equations. We've already got examples of this. We've got 0 for addition in various number systems. We've got the number 1 for multiplication in various number systems. We've got the identity matrix for matrix multiplication. We've got the identity function for composition of functions. So we've got several examples of E. Now, just consider this problem to motivate this little result I'm going to prove. You know that 0 is an identity element for addition in the integers. If I add 0 to any integer, I get that integer back. Now the question is there another integer which also has that property? So we know that 0 works. Is there another integer such that if I add it to any given integer x, I will get x back? In other words, is the identity element in the integers with addition, is it unique? Well, for years, you've been assuming that it is unique, I think. You've probably never bothered, and quite rightly in a way, because of this theorem we're about to prove, you've never bothered trying to find another integer which has the same property as 0. Okay, so we've got 0 plus x equals x, no matter which x you pick. Is there anything else which would play that role of 0? And the answer is no. There's only one element in the integers which has that property. And that's the uniqueness of the identity element. So there's no point trying to find another one. So that's not perhaps immediately obvious. It does require a proof. So let's do that. Is everybody happy with this definition of identity element, in the sense that it's just an abstraction of something that you've been using in various situations for quite a long time? The number 0, the number 1, the matrix 0 for matrix addition, the matrix identity for multiplication, and so on. Is that okay? So let's just prove that such an element is unique. So this is a little, well, I think to call it a theorem would be a bit ambitious, so let's just call it proposition. So let A star be a binary structure. My writing seems to be getting bigger now. Is it visible at the back? Which means I'm using more and more bits of paper, but never mind. Let that be a binary structure, and suppose it, well, let's state it in this way. Then there is at most one identity element for star. So this is uniqueness. You might not have an identity element, but if you do, then it's unique. Now, in fact, most of our examples do have an identity element. We did give one example of a binary structure for which there wasn't an identity element. Can anybody remember what that was? We had an example of a binary structure for which there was not an identity element. I mean, we didn't spend a lot of time on it, but we did mention one last week. Anybody remember what that was? It was slightly contrived, but not too weird. If you just take the even integers, all the integers that are divisible by 2, and think about multiplication of even integers. If I multiply two even integers together, I get another even integer. So that is a binary operation. But there's no identity element for that, because the identity element wants to be the number 1, but the number 1 isn't an even integer. So that's an example where there isn't an identity element. So what we're saying is, okay, there might not be an identity element, but if there is one, it's unique. Which is quite comforting, really. There's no point spending your life looking for another 0, because there's only one. So let's think what we have to prove here. Well, it says there's at most one identity element, which is saying there's either no identity element or there's precisely one. So if there isn't one, we're finished. Okay? It's possible there isn't one, in which case we're finished. But now we suppose there is one and we have to prove it's unique. So suppose that E and E prime are identity elements for star. One of the reasons why I'm doing this proof, well, there's a very good reason for doing this proof in that it's important to know that identity elements are unique, but it's also an example of showing something's unique. It's an example of a uniqueness proof. So if you're asked to show there's only one object of a certain kind, how do you do it? Well, the standard method is to suppose you've got two candidates for the job. So E and E prime have kind of presented themselves as identity elements, and what you've got to do, in fact, is to show that they coincide. So what do we know about E and E prime? Well, they're both identity elements for star, so they're presenting themselves for the job, so they both claim they do the job. So that means that for all x in A, well, E is an identity element, so E does the job. So that's E being an identity element. But E prime also claims to do the job. So in fact we've got 4 equations here, 2 to do with E and 2 to do with E prime, because E and E prime both claim to be identity elements. And what we've got to show using these 4 equations, in fact we'll only need 2 of them, we're going to show that E equals E prime. So although a priori it looked like we had 2 candidates who could do the job, in fact they were kind of masquerading as each other. I don't want to take that analogy too far. Okay, so that's our hypothesis. We're now going to show that E equals E prime. Are my letters getting bigger now? Is that right? I will try and keep them big. So we will show, and there's nothing wrong in a proof at certain points just saying what you're going to do next, because it helps the flow. So when you come to read through it later, it'll help you understand. What's going on. So we're going to show that E equals E prime. And I'm going to be more careful here about writing down the reason why each line follows from the previous one. I've always said the reason, and I've always encouraged you to write down the reasons, but I will actually write down them myself here. Well, I'm going to start with E and end it with E prime. So what can I do with E? Well, we haven't got a lot to play with, really. but I've got to get E prime into the picture. Well, I can write that E equals E star E prime because E prime is an identity element. So if I multiply E by E prime on the right, it doesn't change E. So that's because E prime is an identity element. So I'm thinking here as E as some arbitrary x in a way. It's not arbitrary, it's a fixed E. But this is the x of the, let me just quickly go back to this page. So what I've just done here is use this fourth equation with x replaced by E. So replacing x by E gives us this. In fact, all I've done is use the fact that E prime is an identity on the right. But now I use the fact that E is an identity element. If I multiply anything by E where the E comes in front, I just get the anything back. So that's E prime using the fact that E is an identity element. In fact, all I'm using is that E is an identity element on the left. So this is because E is an identity element. So we started off with E. We then did a manipulation thinking of as E prime as an identity element. And then we used the fact that E is an identity element and we got to E prime. So what we've shown is that E equals E prime. So this is a fairly simple proof. I mean, there's not a lot to play with, so it couldn't be very complicated, really. And we don't use anything about the binary operation apart from the fact that it's got an identity element. So we started with possibly 2, but we've actually shown that they're equal. So if there is an identity element, it is unique, which is quite comforting. So we conclude that there is at most one. As we said, there might not be any, but if there is one, it's unique. And this is a simple proof. It's an important result to just establish once and for all, but it also illustrates this general method of uniqueness proving, that you start off with 2 candidates for the job and you end up proving that they're actually equal. And we'll do that a few times. That's the standard method for showing uniqueness. Okay. Well, perhaps we'll do a similar thing now with inverses. So we haven't actually defined what an inverse is formally yet. So let's do that, and we'll do a similar proof for inverses. That's a bit more complicated. But before I do that, are there any questions about that? So it's a fairly... I mean, there weren't a lot of ingredients in that proof, so we didn't have a lot to play with, but is that okay, the idea of proving something's unique by assuming we've got 2 candidates for the job and just actually showing they're equal? Okay. Well, actually, just before we do inverses, let me just remind ourselves what a monoid is in a formal definition. Because although monoids are not our primary object of study in this module, they're a kind of halfway house between the most general situation and a group. So a monoid, so a kind of word with Greek origins, a monoid is a binary structure A star such that, well, it's not an arbitrary binary structure. The binary operation's got 2 nice properties, such that star is associative, which in fact makes it a semigroup, but it's also got an identity element. Has an identity element. So we will use this word occasionally. It's a useful word to have. So the binary operation is nice in that it's associative. We can't do a lot without associativity, actually. And it's got an identity element. So, for instance, the even integers under multiplication, although they're associative, because they don't have an identity element, that doesn't form a monoid. But almost every other example we discussed last week is a monoid. So I'm not going to write down examples of monoids now, because essentially everything we did last week is an example of a monoid if you look back, because the binary operation was associative and we had an identity element. So that's just for the record what a monoid is. And monoids are important because we often start off with monoids. The first thing we get is a monoid often, and then what we do is this construction I mentioned a few minutes ago. We just throw away all the elements we don't like, and then we get a group. Okay? That's often how we get groups. We just throw away stuff we don't like in a monoid, and then we'll end up with the nice elements which form a group. Okay? And we'll return to that theme a few times. Okay, another definition then, and this is really getting towards the main theme of a group. So we're now going to assume that we've got a binary structure as usual, and we're now going to assume we've got an identity element. So from now on we're going to assume we've got an identity element. So of course, because of our little result that we've just proved, there's only one. So the identity element can be kind of secure, that there's no other usurper going to come along and claim to be an identity element as well. So let's call the identity element E. And let X be an element of A. And we're now going to think about what it means for X to have an inverse or be invertible. So the idea you should be thinking about generalizing here is the negative of an integer, if you're talking about adding integers, or 1 over x as the inverse of x if you're talking about multiplication of non-zero real numbers, or the inverse of a matrix if it's got an inverse. Those kind of ideas we're going to generalize. Then x is said to be invertible. Is that the right way to spell it? I think so. If and only if, well, there's another element, kind of a x's twin or partner. And for the moment, I'm going to use Fraley's notation of just calling the twin or partner x prime. And by the end of today's lecture, we'll be using more familiar notation for the element x prime. So there's an x prime in A, which is going to be like the partner of x, such that, well, if I combine x prime and x in either order, I just get the identity element E. So again, there are two equations, because I'm not assuming that my binary operation is commutative. So there are two equations. Of course, if the binary operation is commutative, these collapse to 1. But in general, it might not be commutative. Just think of matrix multiplication, for instance, or composition of functions. So this first one is saying that x prime is kind of an inverse on the left, and the second one is saying that x prime is an inverse on the right. But I'm going to want both